Hi viewers, in today's class I am going to discuss a very simple topic on antenna arrays. Already in previous class I have just given basic introduction about antenna arrays. Today's class we will go with types of antenna arrays. So basically there are so many types of antenna arrays. Out of those we are going to just pick four and we are going to discuss about them. Basically we have broadside array, endfire array, collinear array and parasitic array. In today's class, we will see an overview of all those four arrays. See in this diagram, you can see broadside array as well as endfire array. After finishing this, I will go with other two arrays. So first of all, we will see what is a broadside array. And basically, this is in short form called as BSA. What is an array? It is nothing but group of identical elements or identical antennas placed side by side or one end of another, just in different ways of arrangement. So here in broadside array antennas, what happens we'll see. Multiple identical elements are placed side by side perpendicular to the axis. Here you need to note down the keywords. Side by side perpendicular to the axis with spacing of lambda by 2 or lambda. Coming to the diagram, see here, these are the different elements of antennas. Here we have taken just 5 antenna elements and see the arrangement how we have placed them side by side. And each and every element is separated with equal distance. And that separation distance either it can be lambda by 2 or lambda. But anyone you have to choose equal separation. You should not take a random separation distance. And here the arrangement of antennas will be like this. Say just we will get with an example of chalk piece also. You can see you can consider these like 3 antennas and these 3 antennas will be just placed like this. And this we call it as broadside array arrangement. And you can observe clearly, for example, if this is the axis of antenna, how are these elements towards axis? They are exactly perpendicular towards the axis of antenna, right? So when we go with these type of arrangement of antennas, we call it as broadside array, where your antennas will be perpendicular to the axis of antenna, right? And in this the spacing can be either lambda by 2 or lambda. And if you see the diagram for this, each and every element will consider like an antenna. And we know that for an antenna you need to apply the external feed, right? How we have to give the feeding to the antennas. Feeding is nothing but input to the antenna. Here different ways of feedings are there. For broadside array, the case we are going to take is equal magnitude and equal phase. That means for first element, how much amount of magnitude and phase I have chosen, the same will be provided for the rest of entire array elements. Okay, this is the important condition for broadside array. For example, say for the first case, I am going with magnitude of 2 volts means just I am saying in an example, for all the elements, I will be providing the same voltage source. And if, for example, we are going with some phase of 90 degrees means for all elements, we will go with same 90 degrees, right? So in that way, equal magnitude and equal phase will be the input in this case of antennas. So for such type of input, how I get my output radiation pattern? See here, for this type of broadside arrangement, this is the way we get our radiation pattern. As this is the axis of antenna, exactly perpendicular to the antenna axis, we will get our output radiation pattern like this. So this radiation pattern, we call it as a bidirectional pattern. And this pattern is perpendicular to the axis of antenna. Here we have 0, 90, 180 and 270. See here where we got our maximus at 90 and 270 degrees. That we call it as maximum radiation is available at 90 and 270 degrees. Minimum radiation at 0 and 180 degrees. Okay, these are very key points that you have to keep in mind. For broadside array, we will obtain our maxima radiation at 90 and 270 degrees plus or minus, as well as minima radiation at 0 and 180 degrees. We may get a doubt, why here maximas and here minimas? See, if you go for the case of two element array sources, we will be adding the field elements. See, everywhere the total field strength is nothing but equal to summation of all individual field strengths. So if you are going to add up all these field equations, finally we will be obtaining the maxima at 90 and 270. That is the mathematical part also we are having. If you need means I will provide in another video also. So here by adding all these field strengths, we will be getting our maximas here and minimas here. Right, this is regarding the broadside array. In broadside array case, all elements will be fed with equal magnitude and equal phase. And here the output pattern will be a bidirectional radiation pattern. Our maximas at 90 to 70, minimas at 0, 180. Okay. Next, we will go with the case of end fire array. So end fire array in short form we call it as EFA. In this case, what happens we will see. In end fire array, there is no difference in the elemental arrangement. See, the same way how we are having our broadside arrangement, this one also will be same. But the difference you can watch in this case is each and every element will be provided with phase shift. The difference between broadside and end fire array you can observe in the application of the phase shift, but the arrangement of antennas will be similar. So in this case, what happens, we'll see. Here, the diagram is provided for front view of end fire array. That's why you can see the tips of antenna like this. In the diagram, it is shown like this. Okay. In this case, it is shown like this, like side by side arrangement. So you can clearly observe from the diagram. Here the arrangement is shown like a front view. Okay. So in this case, what happens? This is our axis of antenna. So when I provide the input section from this antenna end, for example, here magnitudes will be same, but the difference is with the phase. For example, first element we are providing with 90 degrees phase means for next automatically with progressive phase shift increases to 180. For the next element it goes to 270. So equal amount of phase shift is added for each and every element. But if you go with magnitude point of view, it will be same. And here the spacing between each and every element, here we can choose either lambda by 4 or 3 lambda by 4. It's little bit different from broadside case. There we have chosen lambda by 2, but here we are going to choose it as lambda by 4. A slight difference. Okay. So in this case, we are saying that our feed is equal magnitude or amplitude with a phase shift of 180 degrees. But for the case of broadside, it is equal magnitude, equal phase. Only this point is varied for both of them. With that small difference, what happened to our radiation pattern? You just observe here. For end fire array, this is the radiation pattern we are obtaining. In this radiation pattern, what has happened? This is our axis of antenna. You got your maximas along the axis of antenna, and our minimas are perpendicular to axis of antenna. See clearly, this is axis of antenna. We got maximum radiation along this direction and minimas along 90 and 270. And here you can observe just phase differences I have shown. First positive, negative, positive, negative. So for each and every element, some progressive phase shift is applied for the case of end fire array. And this type of pattern we call it as unidirectional pattern. In this case, we get the maximum radiation along the axis of antenna. Excuse me. So for end fire antennas, we can see the maximas along 0 and 180 and minimas along 90 and 270. So broadside array and end fire arrays are quite opposite to each other. In this case, 0, 180 is maxima and minima is 90 and 270. And this pattern we refer it as unidirectional radiation pattern. Okay, these are the major differences we can observe between broadside array and end fire array. And application point of view, there's outside applications. We can use this broadside arrays for broadcasting systems and these end fire arrays for point-to-point communication. So anyhow, a broadside array can also be converted to end fire array with small changes. If you change the spacing of element with lambda by 4 and a progressive phase shift is applied, means automatically a BSA will operate as EFA also. And many applications, end fire array concept is used for helical antennas also. The fundamental concept of antenna arrays can be extended for many practical antennas. After these two cases, we are going with the other two cases, that is collinear arrays as well as parasitic arrays, right? And in outside world, collinear arrays are not used in a wide manner, but parasitic arrays are very, very famous. First, we'll go with collinear array. You can see here the arrangement of collinear array. See here, it's just like a train. If you see some goods train or something, one end to another. Otherwise, we can say one after the other. The arrangement of antennas will be like this. Actually, this is exactly similar to broadside array, but the only difference is the arrangement of antennas. See, in broadside array, I said your antennas will be placed like this, right? But in this case, antenna arrangement will be like this. Or otherwise, antennas will be placed like this, one above the other. We can call it like stack of arrangement also. You can see the difference in arrangements of antennas. That's it, right? So because of that, otherwise everything will be similar to broadside array, even including the radiation pattern. You may get a doubt. Then why we go for collinear arrays? Simple thing. See, when I go with broadside arrangement, the space of antennas is very less. That means occupancy of antenna. But when I am going with the collinear arrangement, see how much space I need to provide for antenna arrangement. And there is more flexibility in broadside arrays, which is not possible in collinear arrays. Collinear arrays, you can arrange in horizontal mode or even in vertical mode also. You can arrange your collinear antennas like this. Right? Any type of arrangement we can do in collinear array. Anyhow, we will be getting our radiation pattern like this. Maxima at 90 to 70 and minima at 0 and 180, right? And collinear arrangement, we'll see just like this. Elements are arranged in single line. See, this point is very important. Single line from an end to another or one end to another. Array can be vertical or horizontal. It can be of any way. Element feeding, I already said, no, it is just similar to broadside array, equal amplitude and equal phase. And here the spacing, we have an option. It can be between 0.3 lambda to 0.5 lambda. And here these type of antennas are mostly called as broadcast or omnidirectional type of arrays. Why? Because for these type of antennas, the output pattern will be like circular symmetry, nearly, not exactly, like nearly circular. That's why we call it as omnidirectional array also. And here, already I said, it provides circular symmetry across main lobe. And here, important point you need to keep in mind is, if you are going to increase the length of collinear array, automatically the directivity gets increased. If you are taking a very small length of collinear array, your result cannot be in a proper way. That's why, because of arrangement of spacing problems, these collinear arrays are not preferred mostly in practical world. And application point of view, this can be used for multi-band and broadcasting purposes. Okay. And finally, we are coming with our mostly used practical antenna, parasitic array. And I can straight away go with an example for this antenna, Yagi-Uda array, a very, very famous antenna. Right. Up to now, whatever all the three types of arrays we have discussed, there is a common point in between them. That is, the length of antennas and size of antennas are exactly similar or same. But as you come for the case of parasitic array, it is entirely different. The first point itself is they are not identical. This is the main important point you have to understand. In parasitic array, there is no rule that elements are equal. So, and elements are not fed directly with which overcomes the feeding problem. See, always a new array is designed means it overcomes the drawbacks of previous arrays. The previous all the arrays what we have discussed, providing feed to the elements is a difficult task. Why? Because if you go for a case of broadside or end-fire or collinear, each and every element is fed individually. See here just 5 elements. You go for the case of 100 elements. Is it possible? Very difficult task. To overcome such type of feeding element problems, these parasitic arrays are designed. So the flexibility in parasitic arrays is, you can see here. See, you can just observe this parasitic array like this. And clearly you can see the variation in lengths of the antennas, even spacing or separation between antennas will be different. And here one more important point, if you have a long view, it gives a trapezoidal shape. The antenna arrangement will be like trapezoidal shape, right? So in this driven element, parasitic element, reflector. These are the three main elements that are present in the parasitic array. First, general meaning of parasitic means simple, dependent on others. That means for these parasitic elements, no input is given directly or no feeding is provided directly. It always depends on the side element, that is driven element. If you take example of a car, in car, the entire car will be moving, but who will handle the steering? Only driver, right? Only driver controls the entire car. Here also same thing. Driven element will be like a driver, all other elements will be like the co-persons, right? So here always driven element size or length, everything will be smaller compared to the reflector element. And parasitic elements will be of still more shorter elements. That's up to our application oriented way we will be selecting. Mostly the arrangement of antennas will be like this. Okay, this is a parasitic elemental arrangement. And here always the input will be given to driven element. Depending on that input, other elements will be operating. And here always your pattern will be unidirectional. Simple thing. Reflector acts like a mirror. Whatever the radiation whatever the radiation that is coming in backward direction will be pushed towards forward direction by this reflector. So you will be getting a unidirectional pattern like this. And these small minor lobes will be always present in all types of radiation, and that can be neglected. So maximum direction of radiation will be in forward direction like this. The fields will be added in this direction for parasitic elements. And here the spacing will be like this, lambda by 4, and a phase of 90 degrees is selected. And here main concept is electromagnetic coupling. This you can clearly understanding in Yagi-Uda antennas. Electromagnetic coupling means nothing but the driven element will be provided feed directly. With the effect of this driven element, this parasitic elements will, because of coupling between these two elements, it also starts providing the electromagnetic field. With the effect of this element, the next element also gets excited. In that way, so many elements get excited in continuous way. All the elements of field gets added and you get a radiation pattern like this. Here, the main concept of parasitic arrays is highest directive gain. And the most used application is television signal receiving purpose, it will be used. So these are the overview of the 4 different types of arrays we are having. See, all these 4 arrays, in practical world, the mostly used one is parasitic arrays. Based on applications, we will be using broadside or endfire. Collinear are used in a very limited manner. Okay. Thanks for watching the video.